In electric circuits, resistances can have complex values. In this case, they are called impedances. When connected in series, the equivalent impedance is given by Z equal to Z1 plus Z2, and when connected in parallel, the equivalent impedance is given by 1 on Z equal to 1 on Z1 plus 1 on Z2. If a circuit has two impedances, Z1 equal to R1 plus I omega L, and Z2 equal to R2 minus I over omega C, find the value of omega such that the total impedance is purely real when they are connected in series and when they are connected in parallel. So, for the first part, the total impedance, or the equivalent impedance, Z, is going to be equal to Z1, which is R1 plus I omega L, plus Z2, which is R2 minus I on omega C. So this is very easy. We just add the real parts and add the imaginary parts. R1 plus R2 plus I times omega L minus 1 on omega C. Now we're asked for the value of omega that makes the total impedance purely real. So purely real means that the imaginary part is equal to 0. So we want omega L minus 1 on omega C to be 0, which means that we're going to have omega L equal to 1 on omega C. So that means omega squared equals 1 on LC. And so therefore omega equals the square root of 1 over LC, or 1 over the square root of LC. And that's our value for omega, which will make a series connection of these two resistances purely real. Alright, so the next part, part B, they're now connected in parallel. So if I have, my formula is 1 on Z equals 1 on Z1 plus 1 on Z2. Now if I make a common denominator here, and then I reciprocate both sides, I'll get Z equal to Z1 times Z2 divided by Z1 plus Z2. And now I can go ahead and substitute in my values. So the algebra here is going to get a little messy. Z1 is R1 plus I omega L. Z2 is R2 minus I over omega C. And adding the two together, well, really we've already done that right here. This is what we're going to get. So divided by R1 plus R2 plus I omega L minus 1 on omega C. And let's get some more paper. Alright, so now we want to realize the denominator of this fraction, which is similar to rationalizing the denominator of a fraction. Here we're realizing it. So the way we do that is multiply by the conjugate of the denominator. So if I multiply the denominator by the conjugate, I'll be left with the real part squared plus the imaginary part squared multiplied by the conjugate, which is R1 plus R2 minus I omega L minus 1 on omega C. Alright, let's move this bit away now. Okay, time to start expanding and simplifying. Alright, so if we expand out these brackets here, what do we get? We'll get R1, R2, that'll give us a real number. What else will give us a real number? Well, if I multiply this term by this term, I'll get the I squared, which will become -1. And since I already have a negative here, that'll be plus omega L over omega C. The omegas will cancel and I'm left with L on C. So that's the real part. The imaginary part will be omega L times R2. so omega L R2, and R1 times 1 over omega C. R1 over omega C. And I still have this bit here, R1 plus R2 minus I omega L minus 1 on omega C, and I just fit. And I divide all of that by this thing on the bottom. Alright, now to expand this out would be even longer and much messier. So what I'm going to do, I'm going to note that this is equal to z, and we're looking for the imaginary part of z, because we want to find the value of omega which will make this purely real. So I want to find what the imaginary part of z is and set that equal to 0. So I'm really only concerned with the imaginary part of this. So the imaginary part will come from multiplying the real part in here by the imaginary part in here, which is going to be, let's see, negative R1 R2 plus L on C times by omega L minus 1 on omega C, and by multiplying the imaginary part here by the real part in here. So that'll be plus R1 plus R2 multiplied by omega L R2 minus R1 on omega C. And then I'm going to divide all of that by the denominator. Okay, and we want the imaginary part of z to be 0. So for the imaginary part of z to equal 0, then really I only need to consider the numerator of this fraction. So let's consider the numerator. I'm going to write this term first, so I can have a positive term first. R1 plus R2 multiplied by omega L R2 minus R1 over omega C minus R1 R2 plus L on C omega L minus 1 on omega C. And that should be equal to 0. Alright, so let's expand this out now and see where we can get with it. So R1, let's write omega L first. Omega L R1 R2 plus omega L R2 squared, and we have minus R1 squared over omega C plus, that's also a minus R1 R2 on omega C minus, okay, what do we get here? We have R1 R2, and I want to write omega L first just because it looks nicer, minus L on C times omega L will be omega L squared on C. Then I'll have minus R1 R2 times 1 on omega C, but there's another minus, so that'll become a plus R1 R2 on omega C, and the final term will be L on C times negative 1 on omega C, and there's another minus, so that will be L on omega C squared, and all that is equal to 0. And there's a few cancellations here. We can see that there will be a cancellation, where is it? Here, R1 R2 on omega C minus R1 R2 on omega C. Are there any others? Not really. Actually, there is. There's one here and one here. Omega L R1 R2 minus omega L R1 R2. So what are we left with? We're left with omega L R2 squared minus R1 squared on omega C. So we've used that, we've used that. We also have omega L squared on C. We've used that plus L on omega C squared equal to 0. Alright, now I want to lose all my fractions. I want to just have non-fraction terms. So the way I'm going to do that, I'm going to multiply by omega C squared. So here I'll have omega squared L C squared R2 squared. Multiplying by omega C squared again will give me minus R1 squared C minus, this will become omega squared CL squared, and this will be just L, equal to 0. Now I can collect the like terms that have omega squared, and here I'll have omega squared equals L C squared R2 squared minus CL squared, and I'm going to bring the other terms over to the right hand side, and that'll be R1 squared C plus L. And finally I can divide by this, and I'll get R1 squared, I'll put the C out the front, plus L divided by, what do we have, LC squared R2 squared minus L squared C. And that is your final answer. That's an expression giving omega, or omega squared, doesn't really matter, equal to this expression. And when it's equal to this, we have a purely real impedance in our circuit. And that is your final answer for the second part. And I've just noticed that I made a small error here. This, when I brought the L over here, it should become a negative, and this means that that is a negative. And so this is our expression. So it's a minus and not a plus. That was just a small error on my part. Should have brought the L over and become a negative L.